Hey everybody, welcome back. It's Ripley again. We're going to do a little mathematical induction today, which is in 12.4 in your book. Mathematical induction is a really cool, really elegant way to prove things like the sum as k goes from 1 to n of k, which is equal to 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 divided by 2. It's going to seem kind of counterintuitive for you at first because there's this weird move in the middle of it. I'm going to ignore this whole summation thing for now because I think it can get a little bit confusing at times, especially with this k thing, but just bear with me. All right, so this is what we're going to prove. We're going to prove that 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 divided by 2. We're going to use mathematical induction. Now, the principles of mathematical induction are very simple. Here's the way it works. In step 1, you just show, oh, I can work with that. Show the equation works for the first term. Term. All right, so in other words, this guy right here, is 1 equal to, this is a question mark, is 1 equal to 1 times 1 plus 1 divided by 2? Well, last I checked, this is equal to 1, and last I checked, 1 equals 1. So check. Now, I'm going to ask that you do it for the other terms, okay? In other words, I want you to do this 2 or 3 times just to get your brain wrapped around how this works. So for the second term, when I add the first 2 terms, I'm going to ask, is 1 plus 2 equal to 2 times 2 plus 1 divided by 2, cancel, cancel. Does 3 equal 1 plus 2? Check. For the third term, I want you to do this 3 times just to make sure that we're not crazy. Is 1 plus 2 plus 3, which we know equals 6, is this equal to 3 times 3 plus 1 divided by 2? Well, 3 times 4 is 12 divided by 2 is 6. Check. All right, so it works for the first 3 terms. Problem is, how do we know that the whole thing doesn't break down at the 17,000th term, or the 56th term, or the 17th term? We've only proved it for the first 3 terms. All right, now here's the big one. This is called the inductive hypothesis, and this is the one that drives students nuts. And I'll clarify this in just a sec. Inductive hypothesis, and hopefully you remember from your previous math studies that if I look at a logical equation or a logical expression, P implies Q, this is called the hypothesis. This guy right here is the hypothesis. Now, here's what we're going to do. We're going to say something that's going to look trite. It's going to look contrived, all right? But it's not. We're going to say, suppose the equation works for K. All right, now you'd say, in other words, i.e. 1 plus 2 plus 3 plus ... plus k is equal to k times k plus 1. Now, all divided by 2. That in and of itself is just a substitution of k for n. I just lost my video. Hold on just a second, you guys. What in the hell is going on here? God, this has been a fucking day from hell. Is there... So, I have no idea. Go here. Is this here? Hello? No. No. God damn it. Seriously? Dude, I'm dying here. I'm dying. This is making me crazy. Oh, there it is. Oh, bitch. All right, so for n, but you got to understand that this inductive hypothesis works in combination with this. Show, with this third step, show that the equation works for k plus 1. i.e., in other words, show 1 plus 2 plus 3 plus dot 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 plus k plus 1 equals, now what should it equal? We're going one term further out. So it should be k plus 1, wherever I see a k I'm just sticking a k plus 1, times k plus 2, all over 2. So this inductive hypothesis step right in here isn't a standalone statement. It's saying prove if this, then this. We're going to show it for this guy. And students often get hung up on that second step. They're like, whoa, Ripley, how are you doing this? Think of it almost like you have a rule for climbing up a ladder. And the ladder's got an infinite number of rungs. Okay? And this is in this case, this is the numerical ladder, as it were. The rule says if I get to any specific rung, then I should get this as an answer. All right? However, if I'm going to show that this always works, then what we're doing in these two steps is saying if I get to a specific ladder, or excuse me, if I get to any specific rung, then I'm sure that I can get to the next rung using the same rule. And since we don't specify that k is 17 or 17,000 or 933, we don't care. We're simply saying that since it works for both k and k plus 1, we have proven what needed to be proved. And guess what we get to write? QED. So watch how this works. It's so easy, but there's always just these little clever steps that you have to throw in there. Okay, so remember how in a logical statement, P implies Q. If I have to prove that, so I'm proving 2 implies 3, I get P for free. This guy's, I always get to work off of that one. All right, so I get to assume that if I see a 1 plus 2 plus 3 plus dot 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 plus k, then I get to substitute this guy in for it. Okay, that's all that I'm saying here. If I see this, then I get to throw this in for it. I suppose it could work the opposite direction as well, but we don't care about that. Well, when I look at this, look at what I got right here. You know, oh, look at that guy. That's a 1 plus 2 plus 3 plus dot 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 plus k. Well, therefore, I get to, because this is a hypothesis. Now, the hypothesis may be wrong. In other words, I may work through this thing and find, oh, truly, this doesn't work out, in which case this equation that we're trying to prove doesn't work out. But that it doesn't, because we know that that equation is correct. There's lots of ways to prove it. All we're saying is we get to take this for granted, and that becomes a really helpful tool. So again, I see a 1 plus 2 plus 3 plus dot 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 plus k. I'm going to substitute in k times k plus 1 all over 2 plus k plus 1, which is this term right here. So I'm saying this part turns into this, and the k plus 1 remains the same. Now what we have to show is, does this equal this? It better. So does this indeed equal k plus 1 times k plus 2 over 2? And if it does, we've proven it, because we've shown that we can always get to the next rung on the ladder, regardless of where we stop. We know that it's going to work for the next one, always. So my job is to algebraically tweak this. Watch. Here's what we get. I'm going to find a common denominator. So think of this as k plus 1 divided by 1. This turns into k times k plus 1 plus 2 times k plus 1. And both of these guys are over 2 now. You see what I did? I just found a common denominator. All right. Now, very much like our trigonometric identities, we're not going to say equals, because that's our job, is to show that it equals. Now, look at this one-step, easy little algebraic trick that we can use here. Notice in the numerator, both terms have a k plus 1. So I'm going to factor out a k plus 1. If I factor out a k plus 1, look at what I'm left with. A k plus 2. And the whole thing is divided by 2, and those two guys are equal. QED. Ooh, with a smiley face QED. I don't know what the heck's going on there. Looks like he's sucking out of a straw. QED! Woo! And we did it. Now, induction, it's counterintuitive, man. I am not going to smugly sit here with a Pharisaic look on my face and say, oh, it's so intuitive. You should get this. You got to wrap your brain around this. You got to play with it a little bit. Let's prove another one of our guys. All right? Let's prove, what was it? How about 1 cubed plus 2 cubed plus 3 cubed plus, I'm going to prove, sorry, interrupted myself, didn't I? Plus dot 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 plus n cubed is equal to, what did we say? It was n times n plus 1 halves squared.